Okay. Okay, let's get started. So, first of all, two announcements before the class. The first one is thank you all for submitting the evaluation. I think we made 90%. I'm not sure. If it was not 90%, it's probably just 87%. So anyway, I gave everyone 10 bonus points. The second announcement is we're going to have the midterm CTF in 2 weeks. It will be in class. So our class will be 2 hours, 50 minutes, right? So there will be 4 CTF challenges. So as long as you understand all your homework, it should be okay. So they are just a modification of the homework. Will not be too difficult. Also, during the CTF, I will sense how you are doing. If I feel most people are struggling, I will be dropping more hints there. And also, before the midterm, I have 2 more office hours, I believe, and also the TA has office hours. And if you want to meet us anytime other than the office hour, just shoot me an email or ping me on Slack. We can schedule another meeting, in person or online, either way. Okay, so today we will keep talking about how do we defeat a stack-based buffer overflow, and also in particular, we'll talk about several defense approaches, and we will look at how do we bypass those defense approaches as well. So before that, let me first remind everyone what is attacker's goals here. Obviously, the attacker wants to take full control of the computer, and usually that's a remote computer, so attacker can only access that through internet. Here, when we say access, probably just some communicating. It could be a web server. The attacker wants to send messages to the web server, like HTTP request, and eventually fully control that machine. When we say fully control, we mean the attacker can run arbitrary code on that victim's computer. In some cases, the attacker doesn't really need to run arbitrary code. They probably want to steal some specific file, but let's assume they just want to run arbitrary code here. So to do that, the attacker needs to somehow hijack the legit control flow or redirect the control flow to the attacker's code. If that code already or the code may be already in the address space of the program, or it could be a program on the computer. All right. So there are several types of overflow. So we can overflow some. So far we have been doing 2 different attacks. One is we overflow a code pointer, a specific code pointer, which is a function return address on the stack. We can also override. Last week we say that you can also override the frame pointer. You do not necessarily need to override the return address directly. Also, in the homework in Crack Me 5, you are actually handling a code pointer on the stack. That's a local variable, it's a code pointer. Let me show you the source code of that. So this is the source code of Crack Me 5. So in this source code, you can see there is a vulnerable function, vulfu, and in vulfu there is it calls memory copy. That's where the vulnerability is from. But in this example, you cannot overwrite the return address on val foo. You cannot overwrite the saved EBP on val foo. However, there is a local variable which is a function pointer. So this in C, this defines a function pointer, and you can just overwrite that 4 bytes. So your input, whatever that is, where 4 bytes will be treated as an address. And this function val foo will just call that address. So you just need to put your sharecode's address as a command line argument here. So you can see that this is another variant of the vulnerability. In this one, you are not overwriting the return address, you are not overwriting the saved EBP, but you are overwriting another function pointer on the stack. So, so all the function pointers, return address, in general, we call them code pointers because they point to code that we are supposed to execute. Also, there are a lot of other objects in the address space we can overwrite, like if you use malloc, you know, they will dynamically allocate memory regions on the heap, and there are a lot of pointers on the heap as well. So some of the objects you allocate may have code pointers inside them, right? They may also have data pointers inside them. We can override that as well. Also in a program like L file, there are other regions like global offset table. We have been looking, we took a look at the global offset table and the linkage table when we talk about the dynamic link part. So in those tables, there are a lot of code pointers. If we overwrite those code pointers, then we may trigger a function call or jump to those addresses, then we can steer, attacker can still take control. So you can see that there are so many pointers in the address space. The risk is very, very high. There are just too many holes in our binary attacker can hack. It's very difficult to protect it. So also we can have a more fine-grained definition of how we can attack or overwrite some value. Sometimes we only have a read permission. We can only read that value. Sometimes we can overwrite that. Sometimes the value do not necessarily is a code pointer, but maybe it's used in a condition, right? So that also influence control flow. So we will see more examples of that. So how do we really defeat those kind of buffer overflow vulnerabilities? So many of you program in high-level languages, other high-level languages like Python, like Java, like Rust. So when you program in those languages, you do not really need to worry about this kind of problems because those languages are safe. They already prevent buffer overflow. But the problem is those languages could be quite slow compared to C, compared to C++. Of course, Rust is making a lot of progress in recent years. Rust is relatively fast compared to Python and Java. It's very, very fast. So even recently, the Linux kernel is introducing some modules developed by Rust. That's for the first time. Rust is getting into the kernel. But still, a lot of legacy code, including the Linux kernel, are still developed by C. So a lot of programs we are using still vulnerable. So to defeat buffer overflow, there are two high-level approaches. One is to directly prevent buffer overflow. So we can prove that buffer overflow will not happen in this language. Another way is to make exploiting it a little bit harder. To prevent buffer overflow from happening is other language, Python, Java, Rust, they do. The cost is, this is a good approach, very good in theory, but sometimes not practical. It could be very, very slow. For example, Compared to C, Java is very, very slow, right? Python is very, very slow. So another more practical approach to protect C code or C++ code there are some indirect approaches. So those approaches do not really work perfectly. They can be bypassed, but they can defeat a lot of attacks. So remember in the last several classes, I list those conditions. How can we, what are the conditions we need to pull off this attack? If you take off one condition, the original exploit will not work anymore. But you can still, as an attacker, you can find another way to attack it. So those are not really direct defense. They are very simple in theory, and for the last 20 years, those approaches have been very, very successful in real world. A lot of approaches we discuss in class, they are deployed on your phone, deployed on your laptop, your desktop. They are used in real world because they are very efficient. Not because they are very, very secure, but because they are very efficient. But like I said, Rust is kind of changing this because Rust is secure and Rust is very efficient. Rust as a language is changing the landscape. Okay, so several examples. We already talked about data execution prevention, like DEP. This is a feature introduced in the CPU like 20 years ago, maybe 25 years ago. So we saw that last week. Even with DEP, we can still, as an attacker, we can still attack this system, right? We can bypass this defense. We can use return to libc attack, or later we can say return-oriented programming to defeat that. Today, we're going to look at another approach called stack cookies or stack canaries. That is also a very popular approach in the last 15 years. All our program, the compilers, by default, they will generate binaries with stack cookies. So far, the programs you are hacking are explicitly disabled stack cookies. But today, we are going to say that we can also bypass that. Okay. So in your homework and in the second part of today's lecturing, you can see we can bypass that. In your homework, you will try that by yourself. Then a direct defense approach is something called a base and bound check. That is an approach used by many languages. So they will instrument a lot of code at the compile time to check where is the base of the buffer, the bound of the buffer. For any pointer, they will check if it is doing legal access. So this is an example. Let's use C as example. Let's say in C we define a pointer. A is a pointer in C. That is just a pointer. In this case, this is a data pointer. This is not a code pointer. So when compiler say a pointer like this, the compiler can generate two more pointers. One is called a base pointer for this, and another one is called a bound for this. So if we allocate some heap memory and let A points to this heap memory, we can do a malloc. So here we ask for 512 bytes, and A points to this. So the code here without that bullet are the original C code, and the others, the with bullets, compiler can generate those code. So when a programmer writes char star A and A equals to that heap memory, the compiler on the behind will set the A base to A as well, and also set A bound. Bound is A plus 512. So it is set. This is the beginning of this buffer. This is the end of the buffer. So every access after that, there will be a check if that access is between the A base and a limit or A bound. And that access check is inserted or instrumented there by the compiler. For example, A0, A511, those are okay, but 512, that's an illegal access. A -1, that's an illegal access. The compiler will instrument instructions to do that check. Obviously, this approach, you can see this. First of all, this can be very slow, and this is not memory efficient. But also, if we just access this may not work because A can be assigned to another pointer, or even A+2 can be assigned to another pointer. So we also, to make this work, to make this secure, we also need to define very complicated propagation policies or propagation rules. For example, when we define another pointer B and assign A to B, the B must have the same base and bound as A. If B, just a part of B, a pointer inside B, point to somewhere inside B, it's assigned to another pointer C. In this case, we also need to set the C space as B space and A space, and the C bound to B and A bound. So the first one seems easy to implement. The second one, obviously, is more difficult to implement at a compiler time. The compiler needs more information to figure out what is the real base and the bound for different variables, right? So if the approach we just saw, you can see the overhead is actually very high. So this is approach some high-level language like Java and Python use. The overhead is very high. First, we need two more pointers. For every pointer, there needs to two more pointers. Even though the programmer do not really specify those 2 pointers, they are inserted there by the compiler. And for any assignment, there will be 2 more assignments. And for any access, like we said, for any access, we need to compare if that's bigger than the base and smaller than the bound, right? So that's 2 more comparisons on any access. So that's why those approaches are kind of slow. For example, this is a paper published in one of the top conferences in programming language. It's called a PLDI, which is Programming Language Design and Implementation. So a paper published 23 years ago. So there are actually many papers in this area. And this is one published in a top conference. And they implement some techniques like that for C language. So obviously, those kind of approaches do not really survive in real world. But those papers prove those approaches can work, just not efficiently. There are also other approaches like this one. Actually, you can see that they are from the same group from Penn. In this paper, they use hardware to speed up those instrumentation. So the software, if you do everything purely in software, it will be very slow. So they cleverly used some hardware to speed things up to make it more efficient. However, the problem with those kind of approaches is those hardware do not necessarily exist on all the platforms we are using, right? That's why new approaches like Rust is very promising, because Rust does a lot of those kind of reasoning, those checks at compiler time. At runtime, it do not do those checks anymore. It does that in a compiler time to make it more secure. So you see, this paper is published in another top conference. We call it ASPLOS. That is architecture support for programming languages and operating system. So that is a conference at the intersection between programming languages, OS, and architecture. It talks about performance issues, security issues, those kind of things. Okay, so that is one of the approaches. Those is one direction to defeat buffer overflow. Next, we are going to look at more efficient approaches that are really deployed. The first one is called shadow stack. So shadow stack is not really deployed on many real-world systems, but this is an approach that has been very inspiring. A lot of our new approaches are based on this, and still there are a lot of research on shadow stack. The idea is actually very simple. Let's see. So because unfortunately right now GCC, I think the latest version of GCC is starting to support shadow stack. But when I made the slides, GCC still didn't support shadow stack. That's why we don't have an example code to show you. But the idea will be very simple here. So this is a picture I took from a 2015 paper, 8 years ago, published in Asia CCS. It's also a very good conference in system security. So this conference always held in Asia, like China, South Korea. That's why it's called Asia CCS. CCS means computer and communication security. So, so we probably talked a little bit about the top 4 conferences in security. Those are IEEE, security, and privacy. That conference probably is the oldest conference in system security. That was has been more than 30 years, I believe. So that conference used to only have that conference at Oakland, California. So when people talk about this conference, we talk about that's Oakland. But right now it's actually in Silicon Valley, so a little bit south to Oakland. Well, Oakland is the perfect place for security conference, right? For obvious reasons. Then the other conference is Unix security. Unix security has a lot of interesting papers on system. Then there's ACM CCS. Another one is NDSS, Network and Distributed System Security. Those are the top 4 security conferences. So publishing in those conferences are very difficult. A lot of topics we discuss in this class, the first paper published in those conferences. And still, now today, if you go to their website to see what papers are published there, you can see they are still working on the topics we discussed in this class. So in this figure, you can see that this is the original stack, what the stack looks like, okay? So when you have a program, the program has many functions, then a function calls another function. So in this case, there could be 4 functions, and the stack may look like this, right? So we assume the stack goes from high address to lower address, and we are using, let's see, this one is actually x86, right? So there is R0 is a function. R0 calls function R1. So R1's parameters is on top of the stack. Then it has a return address, which is part of R0. Then we have the first quarter's EBP. So in this case, R0's saved EBP. So that would be the stack frame of the first function. Then the stack keep going down. When the first function calls the next function, and sometimes there could be local variables on the stack as well if that function has local variables, right? So this is a figure we are already familiar with. Stack goes down there. So you can see the problem here is in this simple picture there are 4 return addresses. Those are 4 code pointers. So if we overwrite one of them, actually any of them, eventually, as an attacker, we can take control of the computer. And the root cause here, like we discussed before, is because we mix the control information and data at the same time, right, in the same channel. So let's say the stack is a channel. We mix control information, like the return address, and also other data, like local variables, on the same channel. So one way to solve this problem is we separate them. To make it backward compatible, the main stack still looks like this. However, at the same time, we maintain another stack, and that stack we call the shadow stack. The shadow stack doesn't have anything else, but only has the return address. So what we have here is we have another shadow stack at another location, and we assume the attacker can overwrite the main stack, but they cannot overwrite the shadow stack. Also, they cannot read the shadow stack. Okay, this is not a very strong assumption. Sometimes the attacker can steal information, can read the value from the shadow stack. That's why the shadow stack, to make this really secure, you also need to somehow secure the shadow stack. Make sure attacker cannot read that. But on the shadow stack, you can have the return address, right? So there are two different approaches. One is called the traditional shadow stack. That is the original idea. So in this idea, the shadow stack is at this location, and it just have the return address one by one. The benefit of this is the memory overhead of this is very small. Right? For example, here we have 4 functions. The memory overhead is just the 4 functions return address. That's very small. But the problem with this is kind of slow. Later, when we say the source code, you can understand, not source code, the binary code, you can understand why this could be a little bit slow. Another approach is something called the parallel shadow stack. So in this case, the shadow stack also only stores the return address. But the return address on the main stack and the return address in the shadow stack, there is a fixed offset. Because it's a fixed offset at the binary level, when you write the code, it will be much faster. So here we can see some examples. Let's say on top, we have the traditional shadow stack. This slide is for the traditional shadow stack. Let's say, so the stack is also in ESP. ESP also points to a stack. By the way, this one is using the AT&T syntax. So the second operand is the destination. The first operand is source, right? So here we have the prologue for the traditional shadow stack. So where do we put shadow stack? So let's assume we put shadow stack at a location called GS, 108. So GS is another general register. So far we haven't been using it, but later you will see we're going to use this. So GS and offset 108 is where we put the shadow stack pointer. So the CPU doesn't directly support shadow stack. So there is no register called a shadow stack pointer, right? So that's why we just use a memory location of that shadow stack pointer. And the memory location is here. Then we move that to the register EAX. Then we move what ESP points to the ECX. So in any function, so this is the function's prologue. So this is at the beginning of every function. So at the beginning of the very function, what does ESP points to? ESP points to the return address, right? So at that point, we haven't set up EBP for the current function yet. ESP points to the return address. So when we move what ESP points to ECX, we make a copy of that return address from the stack to the register ECX. Then we move that ECX to what EAX points to. So we just make another copy of that return address to our shadow stack, on top of shadow stack. So you see, in this case, we add 4 instructions here. And all those 4 instructions are kind of slow, actually. You see, the first instruction that is subtract something from a memory location. That's a memory read and a memory write. The second one is a memory read from the memory to the register. So still we need to talk to the memory. The third one is to, we need to read from memory and put it into a register. The last one is we write something from register to the memory. So all four instructions we need to read or write to memory, so it's kind of slow. So, but you understand how it works. So the epilogue of this is obviously we can, one way is we restore the return address from the shadow stack to the main stack. Or we can directly use what is in the shadow stack. Anyway, we do not trust what is on the main stack, right? So what we do is, first, we move this GS108 to ECX. So basically, we copy the shadow stack pointer to ECX. Then we add 4 to that. So basically, that is a pop for the shadow stack. Then we move what ECX points to EDX. So ECX points to the return address in the shadow stack, which we trust. We think that is not overwritten by the attacker. What is on the main stack is maybe overwritten by the stacker. So we move the address to EDX. Then we move EDX to what ESP points to. So we copy the return address on the shadow stack back to the main stack. Then we do a return. Okay. So this is basically we overwrite. So even if the attacker has the ability to overwrite that return address, when the function returns, it will get the old original return value from the stack. So everyone understand how this works? Okay, good. So another approach is we do not copy and overwrite that. Instead, we check if the value on shadow stack matches the value on the main stack, and if they do not match, we know there has been some attack, then we just exit the program. So the approach is very simple. We first move that shadow stack's pointer to ECX. We pop the shadow stack, then we move whatever stored on that shadow stack to EDX, then we just compare, CMP is compare. We just compare EDX with what ESP points to. Compare what is on the shadow stack and the main stack. So we do not overwrite. So if they do not match, then we know there has been an attack, then we just abort this program, okay? So that is how the traditional shadow stack works. As you can see that, this one is kind of slow. For every function, we have to instrument the prologue and epilogue. So those are at least 6 more instructions, actually more than that. There are many more instructions, many more memory moves, and for this one, there could be memory compare and also conditional jump. So the overhead is a little bit high. I believe someone measured this, and they said the overhead is over 10% for most functions. But you can imagine, if the function is very big, the overhead will be smaller, because you are just instrumenting those instructions. But if the function is smaller, the overhead is high. So some people report that for production systems, the overhead is like 10%, quite high. That's why there is a parallel shadow stack, similar idea, but with this approach, we can have simpler instructions. So you can see the prologue for this can be much simpler, just the 2 instructions. This will be the prologue, so this is at the very beginning of the function. So ESP points to the return address. So, let's see how this one works. So ESP points to ESP points to the return address on the main stack. Then we add some offset of ESP there. That's a fixed offset. You can see that. That's fixed at compile time. So we pop that. So that will be popped into, actually, this one is actually the destination. So the pop here, when we do a pop, you will pop whatever ESP points to, right? So you are going to pop whatever ESP points to ESP plus a fixed value. So this is like one instruction, you are moving from one memory location to another memory location. But the byproduct of this instruction is ESP will increment 4 bytes. You don't want that. That's why you subtract 4 bytes from ESP after that. But still, you only do this in 2 instructions. Compared to the previous one, 4 instructions, this is much faster. The epilogue of this is also similar. You just first add the ESP4, then you do a push this one. So this one obviously is an overwrite case. You are going to overwrite whatever is in shadow stack to the main stack. So the paper reported that the overhead of this is usually only 4.5%, so much more acceptable. Any questions regarding shadow stack? Yeah.
So is that in the same register with the stack pointer, or it really is in parallel partition?
So far, no hardware directly support shadow stack. So there is no, so hardware support a stack, right? So we have a SP or ESP, stack pointer. But no hardware to support that, which means there's no specific register for that. That's why you can say here, we're not really using a register as a shadow stack pointer. So the shadow stack pointer, in this case, is a fixed location at the current stack pointer plus this value, in this case. That's a memory location, right? Also, in this case, the GS 108, this is also a memory location. This is also a register, yeah. So there has been a lot of research on shadow stack. Even my team, we do research on shadow stack. Several directions for this is how to make it even faster, how to make it even secure. As you can see, those approaches, the shadow stack and the main stack, they still live in the same address space. If attacker can overwrite the main stack, the attacker maybe can also override shadow stack. So the assumption here is shadow stack is secure. So that assumption is not really strong. Because of those reasons, and also the overhead is quite still a little bit high, shadow stack is not really used very often in real-world systems. But it's getting into real-world systems. I see a lot of compilers starting to support shadow stack. Another approach we are going to look at is called stack cookies or stack canaries. This is an approach that is widely deployed in our systems. All your phones, all your laptop have this deployed. Yeah. So the original paper of this approach was published in Unix Security, one of the conferences I just mentioned. It's a top 4 security conference. It was published back in 1998, and the title is Stack Guard, Automatic Adaptive Detection and the Prevention of Buffer Overflow Attacks. Actually, 15 years after this paper was published, in 2013, this paper won Test of Time Paper Award at Unix Security. So 15 years after the published paper, they got an award. So which shows that how important this approach is. Later you can see this is a super simple approach. That there is no fundamental theoretical contributions. It's an approach that everyone can easily understand, and this is also an approach we can bypass for some cases. But it is widely deployed. It is used in all our systems. That's why it gets this award. It's not perfect, but it has been protecting us for a very long time. So getting the test of time paper award is very difficult in those Big Four conferences. Actually, in our department, Professor Marilla Blanton, she has a paper published in another top conference called ACM-CCS, and that paper also won Test of Time award. I think that's 10 years after that paper was published. It's extremely difficult to get that. So in short, this is a compiler technique that attempts to eliminate or make buffer overflow much harder to exploit. This is not a direct approach, so it doesn't really tackle the root cause. It doesn't remove buffer overflow. Buffer overflow still exists, but make it much harder to exploit. So this technique doesn't require the developer to modify their source code in any way. So you have been developing C programs. When you develop C program, you never thought about this, right? Because compiler instrument code directly. So that's what security guys do. A lot of our solutions we develop at OS level or compiler level. So the developers, they do not really know what a compiler does that to protect their program sometimes. So similar to the shadow stack approach, in this approach, the compiler will automatically patch the function prologue and epilogue. The prologue, the code will simply push an additional random value to the stack. So we push a random value between the saved EBP and local variables. So you can still overwrite a local variable. If you want to overwrite saved EBP or return, you will also overwrite the pushed random value. Then in the epilogue, the program will check if that pushed random value has been changed. If it is changed, then we know there has been a buffer overflow attack. That's the idea of it. Super, super simple, okay? So let's look at this example. So this is a return overflow 4. So this is the source code we have been looking at, and we hacked it multiple times. We use different compiler options to compile the source code, as I showed you last week. Let's say, so today we are going to look at a version we haven't looked at. So it's in buffer overflow. It's in overflow 4. So you can, if you can check this is our, well, I'm not really sharing you guys the source code, but I'm showing you, this is a make file. So we are using the same source code as a main.c, and we compile it with different options. So at the very beginning, we compile it with no stack protector. So that means we disable stack cookies. We also use executable stack, so you can inject the shellcode there. So last week or 2 weeks before, we were using this one, right? So this one, still there is no stack cookies, but we do not allow you to execute the program on the stack anymore, okay? So today we are going to look at is this version. You can say this version, we do not give it those flags. So this is actually the default version. If you compile your C code now, this is the default one, okay? So the M32 means we want to compile this as a 32-bit program. Like here, without that M32, then it's a 64-bit program. So there's no stack cookie. You cannot execute the program on stack. So for this one, then we can compare the binary code of this. This is the very first version you look at. It has a push EBP, move ESP to EBP, then just set up the parameters for, this is a string copy, I believe, maybe string copy. So the same source code after we compile compile with stack cookies will look like this. So you can forget about this one. This one is about PIE, so it's not related to what I want to say. So the main difference is the instructions in the red box. As you can see here, the first instruction is we retrieve 4 bytes from a memory location which is GS at offset 14. GS is a general register. GS points to a memory location. From that memory location, offset 14, which is 20 bytes, we get 4 bytes, and we move that 4 bytes to ECX. And that 4 bytes is the stack cookie. Then we push that 4 bytes. So here we're not really using push, we're using move. We move that 4 bytes into a local variable, right? This one looks like a local variable, EBP minus C. That's below EBP. So EBP points to saved EBP. So EBP minus C, then we put 4 bytes there. And that 4 bytes, like I said, that's a stack cookie. So when you create this program, the shell, the operating system, generates 4 bytes of random value. Actually, it's 3 bytes of random value plus 0. So it's, but in total, it's 4 bytes. Generated that 4 bytes, put that 4 bytes in this memory location. Then each function will retrieve that 4 bytes from that memory location, put that 4 bytes on its stack. So that 4 bytes has to be generated at a runtime. It cannot be generated at a compile time, right? That's why you cannot directly, you cannot have an immediate number here. If it's an immediate number generated at compile time, then everyone analyze the binary will say what that value is, right? So after that, we just clean up ECX. Then the same instruction here. So after everything is done, before we are going to return, what happens is we are going to move that EBP minus C, the stack canary on our main stack to ECX. Then we compare ECX. We do an exclusive OR to compare with the original stack canary value at GS at offset 14. If they are the same, which means there is no attack. If they are not the same, means there are attack. So if they do not equal, we are going to call this function. We are going to call stack check fail local. So this function will exit the current process and print out smash stack detected. Okay? So let's look at this program. Let's say, for example, here. What is the size of our buffer? The size of our buffer is EBP minus 13 hex, which is 48 bytes, right? You will have been doing that. You can say here, let's say the buffer is at 34, which is 52 bytes. Okay. So yeah, before we look at the stack, I'll remind you what is GS or FS. Those are also registers in the x86 architecture, but we haven't used those registers so far. So those registers actually exist in very old CPUs, starting from 83, 86, okay, like 40 or 50 years ago. Those CPUs started to have those registers. We used to use, before virtual memory, the CPU used another approach to segment memory. That's called segmentation, right? You probably learned that from your OS class. So to do segmentation, you use those registers. So look at those names. It used to be code segment, CS, stack segment, SS, data segment, DS. So, but right now we're not really using segmentations. We're using paging. So that's why those registers we're using for different purposes. So GS we're using for threat-related information there. Okay. So this is what the stack looks like for those two different versions of the same C code. The old version, we have return address, we have saved EBP, EBP points to here, then we have buffer, which is 30 bytes, not 30 bytes, 48 bytes. However, for the version with cookie, this is what the stack look like. You see that we put the canary or cookie at the location EBP minus C, right? So those 4 bytes are reserved for the canary, and the buffer is actually at EBP minus 34 in hex. So based on that, we do a calculation. We can say between buffer, the beginning of buffer, and the canary, there are actually 40 bytes. In the source code, we ask for 30 bytes. Okay, so the compiler actually gave us a little bit more, gave us 40 bytes there. So the canary is only 4 bytes, but the canary to the saved EBP, the total here is C, which is 12 bytes, which means there are another 8 bytes in the middle, no one really use, okay? So let's do a simple demo here first, before we look at the overhead. We are looking at program, this one. So from the slides, from the binary code, you already see that the buffer actually is 40 bytes. So if we input 40 bytes there, it should not have any problem, right? That's a buffer we can, so this one takes from standard input or where? I don't remember. Oh, this one is standard input. So we just do Python 2. Let me check if the syntax is correct. Okay, so this one will print 40 bytes. It will not add anything there. Okay, so if we give 40 bytes to the program will not crash or anything. The program will give 40 bytes to it, even though it's bigger than the buffer in C code, but it's not going to overwrite anything. So we are going to print out IPT the full. But if we give 41 bytes there, we are going to overwrite 1 byte of the canary. Okay, we are going to overwrite A there. Unless that byte is already A, we are going to have some errors, right? So there is a chance, one out of 256, there is no error, right? So you can see, when we overrun 1 byte, the program will detect there is a buffer overflow attempt, and it will say, so the C library function, this is a C library function, stack, check, fail local. That C library function will just crash the program and output this specific string. Stack smashing detected, terminated. Okay, so that's why if you giving more, it will also crash the program. So this is before the return instruction is executed. The return instruction is here. The return instruction is how we exploit the previous version. But before that, the program already detect it has been attacked. So that's why buffer overflow will not work in this case. So to debug this program, we can. I want to show you guys the stack canary is every time is different. When you create a new process, it's different every time. But that canary value stays the same in the process life cycle. So far, it stays the same. So all the implementation right now, it stays the same. So obviously, you can make it more secure. You can, at least at a fork, you can re-randomize it. But right now, current system not doing that. So we can say this by just debug the program at this. So let's see. It's a breakpoint on main. I think we didn't install the plugin. Let's see if we can just examine GS. I think it's GS14, right? GS14. How do I do this? Oh, probably we need to do 2 steps. We print out the GS. No register. Oh, we're not running yet. Okay. Now we're running the program. So now we print out GS. So that's valid. GS plus 40. Okay, I don't remember how to do that, so let's use another approach. Sorry about that. Let's set a breakpoint at val foo. So now we continue the program. Now we are in val foo, and we set a breakpoint here. Let's set a breakpoint here. So we are about to get the stack cookie and move that to ECX. So after this instruction, ECX will have our stack cookie. So we just print out ECX. You can say, you can say our stack cookie, the value is C1, A8, CB00, okay? So in this Linux system, the least significant byte of the stack cookie is always 0, okay? Remember that. So only the other 3 bytes are random. For 64-bit machine, you can say 7 bytes are random. The least significant byte is 0. So that is the stack cookie. So if we rerun the program, I'm not sure, or we need to re-debug that. We continue, then we no, this is not where we're at. We need to do another continue. Then we do. Say, when we rerun this program, the stack cookie is changed. Now the last byte is still 0, but the higher 3 bytes are different, right? So if we go to the 64-bit machine challenge, we go to the 64-bit. The offset for 64-bit will also be different. So let's disassemble this. In this 64-bit, this is a stack canary. You can see that In 64-bit, we're not using the register GS. Instead, we're using the register FS. Okay, that's a difference. But you can say the cookie is stored into RAX. Then RAX is saved to RBP -8. Okay, so that's where. So this one, they are not really wasting any space. Right after the saved RBP, we have 8 bytes of a stack cookie. Right. So if we debug this program, we want to set a breakpoint at here. Yeah. So, yeah, let's set a breakpoint here. So after this instruction RAX, we'll have our stack cookie. Then it will be saved onto the stack there. So we just set a breakpoint here. We run this program. We just print out what is in RAX. So you can see the last byte is 0. The first 7 bytes are random. We run this again. It's a different value. The last byte is 0. Other bytes are changed. Okay, so that's a stack cookie. So this one takes from, okay. So I just showed you the 64-bit version. The C library function name changed a little bit. Stack, check, fail, almost the same. Okay, so the overhead of this, you can say there are still many more instructions. How many instructions are there? 6 more instructions. So 64-bit probably 7 more instructions. Well, of course, this one, when there is a attack, then the overhead doesn't matter, right? So the overhead is about if there is no attack, what is the overhead? Okay. So those are the 2 different memory locations for 64-bit and 34-bit, 32-bit. GS and FS, those are general registers. So the random value is generated when the program is created. Then it's stored in that global variable. That global variable is pointed by GSFS. So actually, it is stored in a data structure called thread local storage, TLS, not transport layer security. It's a thread local storage. So some of the debuggers, like PongGDB, they have a command TLS to help you debug this, but I just tried there. We didn't install that on the server, but on my local machine, I actually installed this. But anyway, so for the canaries, like I said, it's supposed to be a random value because it will be, if it's a random value, it will be difficult to guess that value. But there are some other ideas to have this canary. For example, you can just have all zeros. If you have all zeros, obviously some of the vulnerable functions like a string copy will not be able to copy that, right? Because it's a 0. When you have a 0, it stops there. So it still cannot override, save the EBP, or return. And there are other approaches using other terminators, like a new line, Canary, those characters. But still, the most Canary value we say is still random values. All of them, they have different advantages and disadvantages. So since the paper was published back in 1998, this approach was quickly introduced into GCC 2.7. So you can see the stack canary approach is even easier than the shadow stack approach. But it's not as secure as shadow stack approach. because we're going to say how we can bypass it after we come back from a 10-minute break. But this is very easy to implement. The overhead is small. That's why it has been used since. Also, there are other approaches developed based on this. For example, IBM developed something called Police. It will place buffers after local pointers in the stack frame. So you see the problem of the approach we just saw. It can protect the saved EBP and the return address. But if there is a buffer, then there are some other local variables. Then the buffer can still override other local variables, right? So in this approach, in the IBM's approach, it will place buffer right below the stack canary. Then will be other local variables. So your buffer, if you have a sequential override, you don't have a chance to override those flags. I will have some slides to show you how it works. Also, 2012, Google implement stack protector strong. This is another. So you saw in my makefile, I'm using stack protector, not the strong version. So strong version will make it. So I'm not sure what does strong version do. I know what the stack protect all does. So if you use stack protect all the functions will be protected with the stack cookies. So if you use stack protector, it will not instrument the protection to all the functions. For functions that are small, it will not do that. The reason is the overhead will be too high for with small functions, right? But it's always a trade-off between security and the performance. So that's why stack protector all will protect all of those functions. Also, the Ubuntu system we're using right now, the default compile is the stack protector. And for Arch Linux, they actually their default protection is default flag is stack protector strong. Okay, go back to that IBM approach. So this is a function valfoo. The function has those variables: integer a, a pointer b, and two buffers. Buffer basically is an array of string of characters. Then we can say there is a string copy, which is a variable. There is another string copy, which is also variable. So traditional compiler, how do they place those variables? They will just follow the order those variables are defined in C. So the return address, after return address, we have saved the EBP. Then the local variable A will be here, then will be B, then the buffer C and D. Okay, that's it. So it will just strictly follow the defining order of those variables. So the IBM approach is they will reorder those variables. C and D will be placed at higher addresses, and A and B will be placed at lower addresses. So you can still override D, you can still override C. So D can override C, C cannot override the Canary anymore. If you override Canary, it will crash. But you will not have a chance to override A and B, right? So that's just the simple approach. So a little bit more compiler time calculation. Okay, so next we are going to talk about how to bypass this. Then this is also your homework. You will bypass this. So let's take a 10 minutes break. When we come back, we talk about this.
Psychiatric Associates. Calling to remind you of
Okay, let's see how we can bypass this stack Canary mechanism. So basically there are two approaches. First one is somehow you can find out what is Canary value this process is using. Maybe it's through a lot of vulnerability. Through maybe there is an arbitrary read vulnerability in the program that you can utilize to read any memory location of this program, right? And we know that the Canary is stored at a specific memory location, the GS plus 14 or FS plus 28, right? So if you have that kind of vulnerability, then you know what that is. Then you can input that, when you do that buffer overflow, you can input that Canary value back to it. So you overwrite that with the same value. You still overwrite it, but with the same value. So it will not cause any problem. Another approach is approach we use as an attacker, we use that approach a lot. We just brute force. We just guess. We just guess what that value is. So in 32-bit version, we know that the least significant byte is always 0. So technically, we only need to guess 3 bytes, right? You say that, the last significant value is 0. We only need to guess 3 bytes, which means there are that number, 16 million possibilities, okay? It's possible, we can guess. So if it takes 1 second to guess once. That's like almost 200 days to guess the canary. Right? So is there a smarter approach to guess this? So here we are guessing those 3 bytes as a whole, right? So we don't really need to guess that 3 bytes as a whole. As you just saw what I showed you in that example, when we overwrite 41 bytes there, we actually only overwrite 1 byte into the canary, and it generates a fault, right? So it means we don't have to guess those 3 bytes together. We can guess those 3 bytes one after another, right? We guess the first byte, so it will take us 256 guesses. Guaranteed, we can guess it right. 256. Worst case, 256. Then we guess this, then we know what is the first byte. Then we override the correct first byte. Then we guess the second byte one by one, right? So in total, we only need 768 guesses to guess those 3 bytes. So obviously for 64-bit version, where we're double the time, will be like 1,600 something times. But still, it's much more doable, right? It's much more doable. So that's what we're going to do in this class and in your homework. You only need to do this in the 32-bit version because it's basically the same thing. It's just 64-bit. It will take a much longer time. So this is the program. This is a valuable program. So far, this is the most complicated program in our class. So let's try to understand this program, and we're going to attack this program. In this program, we have a main function. The main function is a big while loop. Then there is a while foo, several global variables. In this big while loop, we first will fork a child process. So you took OS class, some of you took OS class before. So the fork eventually maps to the system call, also called fork. It will make a copy of the current process. So the child process and the parent process will keep executing, but from different place. If the fork function returns 0, it means this is the child process. If the fork function returns another number, in this case, I don't care what the number is. That is actually the child's PID, process ID. In this case, I don't care. So in that case, that will be the parent. Okay. So this resembles our web servers. A lot of web servers is designed this way. The web server has a parent process. It will listen to TCP collections. When it receives a TCP collection, it will create a child process to handle that TCP collection. And the problem is here, is a fork. So far, the design, when a process is forked, it will not regenerate the stack canary value. So the child and the parent, they will have the same value. So in this case, the parent will just print out its own process ID. It will use a system call getPID to get its own ID, print out parent ID, then it will just wait for its child. It doesn't do anything else. So the parent is not what we are attacking. We are really attacking is the child process. And there will be a lot of child process being created. So in the child process, what we do is first we print out the child process ID. So after that, the child process will call the function while foo. If while foo successfully return, it will print out IPT the full. So after that, the child process will just exit. Okay? So after the child process exit, the parent process will wake up from here. Okay? So after the parent process wake up from here, the parent process will go back to the while loop. It will do the fork again. So every child process, they will not execute the loop, okay? Only the parent will execute the loop. So the logic here is very simple now. You should be able to understand now. The parent will create a child. The child will call valfoo. If the valfoo returns successfully, child exit, parent create another child process. The child process do the same thing, okay? Then in the child process, when it calls the valfoo looks like this. It has a local variable buffer. It has a file pointer. It's trying to open a file. It's trying to open a file at a specific location, temp exploit. This is to simulate we are getting some input. But now I'm not using, I didn't program socket here. So we put the input into the temp file, a specific name, temp exploit. You need to put your exploit into this file. So the child process will keep looking if that file exists. If that file exists, it will just read that file, use fread, read that file into a global buffer, which is 200 bytes. Then it will copy, let's see, it will do, this is a variable function memory copy. It will copy whatever is in that 200 bytes to the local variable buffer, okay? So now we're back to our traditional buffer overflow problem here. The difference is this program is protected by stack Canary. So after that, the child will close the file descriptor, remove that temp file, and return 0. So after it returns, it will show IPT the full. Okay. So to approach this one, we can still put the shellcode in environment variable. What we want to do is overwrite the return address of valfoo, but before that, we need to figure out what is the correct Canary value, right? So let's do a quick demo here first. So for this one, I actually recommend you to use 2 terminals. So to do that, we installed Tmux for you on our server. It should be bypass 32. So when you go to the terminal, you type Tmux, then you can have multiple windows here. You do Control B, %, then you can get 2 terminals here. So if you don't know how to use Tmux, I have a cheat sheet on my website. So now you can see, if we run this program, it will just print out the parent ID and child ID. Why is that? Nothing else, right? The program is still running, by the way. So you can see there. So when we run this program, we didn't give any input. So the parent will print out the parent ID, then wait there, right? Then the child will print out the child ID, then go to valfoo. So you can see the parent ID there, child ID there in the terminal. Those are printed out by 2 different programs, 2 different processes. Then the child program here, the child program right now is not returning because it's looking for this file. The file is not there, so it's in this loop. Okay. So if we create something in that file, let's say. If we go here, let's echo just some random thing to the temp exploit. Okay, so what will happen is this value will go to that file. The child process will read that value, but we're not going to trigger any. So it will read that file. Then they will do memory copy. Then you close that. It will remove that file. Then nothing, just returns. So the child process will print out IPT the full. Then after that, the main process will print its ID again and create a child process, print its ID, right? So we go back here, we do this. You can say the child process print out the child reads 7 bytes. That's our 7 bytes. Maybe there is a end of line thing there, and it doesn't really guess any Canary instead. Then it print out IPT the full. So in this case, how big is the buffer? Do I have a slide for that? Oh, I do have a slide here. So the buffer in this case is actually, oh, this is different from one. Well, anyway, the buffer is actually 40 bytes. The Canary is at EBP minus C. So which means if we input more than 40 bytes, we're going to let's say we just use Python. So 40 bytes, we put this to temp exploit. 40 bytes is actually 41 byte because the ending probably is a new line, A in hex. So here I input 40 bytes, then 40 bytes of A, then another byte will be, so it will read 41 bytes. So hold on, let me confirm what is that last byte. Oh yeah, see, the last byte is the A there. Okay. So that last byte, the A, new line, will be overwritten to the first byte of the Canary, right? So that's why it's believed we are reading A. So that A is not really this A. It's a little bit confusing. Let me do B instead. Let's do C. Okay. Okay. So that A is actually hex A, which is the end of this one, that A. Okay. So you can say, when I input 41 bytes there, the last byte, which is hex A, will be the first byte of the Canary, and the child will print out, we guessed A there. And because of that, because that byte is not A originally, so stack smashing detected. So we can also guess more. Let's say, if we do 42 bytes, then we will be overwriting 3 bytes, right? So those 3 bytes will be 0A, 6363. So that is the ASCII value of, this is also hex, the ASCII value of C there. Let's see. Oh, by the way, the order I printed out, I printed the least significant byte first. Okay, so now do you understand this program, how this program works? Any questions? Okay, you guys are smart. Good. Okay, so now we want to attack this program. We want to guess that and put the share code there. So the first step, let me have a clean environment first. I want to have a clean environment. Bypass 32. The first thing we do is we still set up the share code in the environment variable. So where is it? Let me write this one. We still want to jump to our return to our share code. Yeah, 500 should be enough. Okay. Okay, so this is our share code location. We have a 500 lobsled. Looks good. Then our exploit, what should our exploit look like? Our exploit should look like 40 bytes of garbage, right? That matter. 4 bytes of Canary has to be correct, which we are going to guess. Then after that, in between, there are 8 bytes of garbage. Then another 4 bytes of garbage. The return address should point to our share code, right? So then to do this one, obviously, we have to write a program to guess. So I wrote a script to do that. It's not a perfect script, and it's your job in the homework to make it better. Okay. But I will show you it works, and I'm not going to share the script to you, but I'm going to show you. So if you want to reuse that, you need to type by yourself. Yeah. So where is? So this is my simple script. My script will only guess 1 byte. It's not fully automatic. After I find 1 byte, I have to update it a little bit to guess another byte. So it's not fully automated. So you can make it fully automated. So let's go to here. So now we can have 2 terminals. Let's see if we have this. That's right? Print environment variable should be. It's not readable or something? Okay, looks like we have, because I need to make sure, you need to make sure for both terminals, the share code is there, right? If you create a tmax first, then do that export, you may only have a share code in one of the terminal. Then, what do? We create a new file. Let's call it temp exploit.python. Then that's a file we cannot execute, right? So we need to change mode +x to make it executable. So temp ex.python, right? Then we can use my code there. Temp. So I'm just going to copy this one here. So it's a little bit big. Okay. It's too small. Okay, let's take a look at my script. So how does it guess this? So my script will, first of all, it will execute as Python 2 script. It has some libraries I use. In the main function, there is a loop. So C1 is a value, integer, from 0 to 255. So basically, that's 1 byte value, 0 to after. So for that one, then we're going to check if that exploit exists. So then we need to change this. Temp exploit. We check if that exploit file exists. If it exists, we will just sleep. So the purpose of this is to wait the child process to read that and delete that. Because we use that file to communicate, right? The child process will find this file, read that file, and delete this file. If this file exists, we're not going to write anything here. So we wait. So if it doesn't exist, we're going to open that file. And open here is basically create that file. We're going to create this file. Then in that file, we're going to write, this is our exploit. 40 bytes of garbage for that buffer. After that, we should have, this part we don't need right now. Eventually we will need this. So what we need will be, so here will be the first byte we guess, right? And we are guessing from 0 to 255. So we are going to, this is a syntax. This means this is a byte. Then C1 is, I think I missed one. Okay. Do you guys understand what's going on? So 40 bytes of garbage, then 1 byte more from 0 to 255. So that's why you see this script is not fully automatic. After I correctly guess the first one, I need to change this 9 a little bit, right, to guess the second one. So let's see if it works. Now we go to let's go to the second terminal. The second terminal, we just, so far we don't need the share code. Where is it? Second terminal, we run this program. The first terminal, we run our script, which is at exploit. Let's see if it works. Oh, it works. Now we start guessing the canary. So when it's not successful, it shows stack smashing detected. When it successfully guessed that, it should show IPT the fool, right? So when you say IPT the fool, we will stop the guessing part. We don't stop this part. Okay, the server, the parent process always run. If we stop this part, we restart it, it will have a new canary, right? So we are already guessed 30 something.
So this will get 0, right?
What?
You are checking for the 0 last.
Oh, yeah. This one is 0, right?
For the first 2.
Yes, you're right. So let's stop this. Let's stop the, we're here. Let's stop this one. So the first one, the very first one should be, let's see. Oh, yeah, you're right. See, the first one is IPT the fool. That's a 0, right? So we actually should be start guessing from the, so here we can have, the first one we know it's 0, so it's just 0, 0. Then we start from guessing from the second byte. Yeah, that looks good. Okay, the server is still running. I didn't stop it. We just changed our script. Oops, sorry. This part I need to quit, otherwise you cannot see what's going on. Does that matter? Okay, go back here. Okay. So what is the order I printed? Oh, okay. That's the right order, yeah. So the last one is 0. Okay. I don't know what the Canary value is, so we have to wait. So the guessing is so slow because my program, I have 2 sleeps there. It's always 1 second. For other programs, it doesn't have to be 1 minute, 1 second, right? Depends on how do they communicate. In this case, we communicate through the file system, so it's a little bit slow. We guessed more than a quarter. Or half. We're not lucky. It's a big number. So you can see the charter process, the ID is increasing. Yeah, it's a new process and a bigger PID. Is something wrong or we're just unlucky? Or did we miss repeated 4? So you see, looks weird. Not getting it. Oh, it's really a big number. See that? It's EC, right? It's, where is it? It's EC here. Yeah, we were just unlucky. It's really a big number, EC. So after this, we can go back to change our script. So now we know the second byte is EC. So we can guess the third byte. We go back here. We keep executing this. Hopefully we get lucky this time earlier. Well, the worst is FF. And we got EC there. Of course, you can also write a program to have a multi-thread to guess at the same time. Oh, but they share the file. That's a problem. Yeah.
Professor, we can have like multiple copies of that file, right? Anyway,
Well, the thing is, they share one file, right? They do not use other communication channel. Yeah. If it's a real web system, they use socket, then there's no problem, right? Oh, 3D, right? This one is quick. We have 3D here. So this byte will be 3D. Then we only need to guess the last byte. Okay, another big number, AB there. Okay, so now what do we do? We have everything we need, right? So here, we don't need to guess anymore. So this one is AD. That's the full Canary. We can try this. So when we do this, it should not have smash stack detected, right? When we just input that, it will just because we're keep writing that, so it will just show IPT the full always. Keep showing IPT the full. I think so. Right? It shows IPT the full because we already have the full 4 bytes of the canary there. So then how do we construct our exploit? Let's say we are right here. So we have the canary. So after that, we have 8 bytes. After that, we have 4 bytes. So basically, we need 12 bytes of garbage for the saved EBP and the 8 bytes in between. Then the return address. That's it. So our shared code should look like. I can just reuse this one. I can use another 12 bytes of garbage and the address. So what is the address we have? DCA1. DCA1. So DC. Let's do DC DD. Should be okay. Because we only have 500 bytes of lobster. Okay, now we run our exploit again. Hmm? What's going on? I think it's syntax. Right? Oh, I missed a plus sign there. Right? I think that's it. Okay. See? That's how we get that child process give us the flag. And if we do a PS, you can see that those are 2 processes. One is a child, one is a parent, because right now there is another new child executing. So maybe this one with a smaller PID is as a parent. So the parent is executing as root. The child is also executing with root. So previously we saw that if we call the system call exe save the child will not have the privilege. But in this case, we are not using exe save we're just using fork. The child will have the same root privilege in this case. Okay? Get it? Cool. So for the rest of the class, you can work on this. You can start working on the homework. This is part of the homework. I think this class we only have today's class we only have one programming or hacking assignment. Is this one? Yes. So we only have this one, but I will give you 9 points of bonus points if your script is fully automated, not like my script. Okay. If which means you need to read the output from the other terminal. If your script is fully automated, 9 points bonus. Got to upload that. Okay, obviously you don't have to use Python. You can use any language you are comfortable with. You can use C, Perl, whatever you are comfortable with. And it's also very easy for me to check if you are cheating, because if you have the same Canary value, the chance you guys have the same value, what's the chance? 2 out of 16 million, right? So. Okay, if you don't want to work on this now, you can leave, I guess. It's okay. So, yeah, Kevin. So, which year are you? Are you undergrad or master?
Oh, master, second semester.
Second semester. Okay. If you are interested in hacking, we actually have a hacking group meeting every Friday.
Every Friday.
3 to 5. Yeah.
Good. Oh, okay, can I like leave early because I got four.
Yeah. Yeah. That's yes. It will be 3388 conference Davis Hall.
338.
8. Yeah. Yeah.
It will be like very advanced thing.
Yeah. That's easier than this class because most of them are freshmen.
Oh, okay.
Yes.
Oh, you mean like undergrad freshman?
Yeah.
Three, three, eight, three, eight, three,
3388. Yeah.
3 to 4.
3 to 5.
Oh.
It will for you. Yeah.
Sounds good. Thank you very much
Sure.
for inviting me to.
Sure.
See you next time.
Sure.
When will you execute? Let's say.
Okay, give me 1 minute. I'll reply this email. Give me 1 minute. Yeah. Yep.
So, you said this is a generic stack for a function, and whenever different function calls, we put on the bottom actually,
Mm-hmm.
like in the lower address.
Yeah.
So, every function needs some libraries to call like steady.
Yep.
So, this will be there for every function, or there is only one instance of this and.
Well, most functions. Well, let's just say every function. Yeah. But this is dynamically changing, right? The thing is, it's dynamic. It's not static. Let's say you have that function. You say start main. And this function calls main. Then your main function calls one, let's say b. Okay. Then after it calls b, it calls c. Okay. Then c calls printf. What do
Or
you mean a
lib-
separate instance of libc?
libc are the libraries of
Well,
which is needed for
you mean the code or
I mean
the
Yeah.
stack frame or the code?
stack frame. Yeah.
It
Read
would-
on the stack
so-
frame of P.
So every thread has its own stack. Okay.
Yeah.
So if this one is one thread, they have their own stack. So far, all the programs we're looking at, they only have one thread. So it doesn't matter. So you want a program, so far for all programs we're looking at, a thread is the same as process. They only have one stack. If it's a multi-thread program, then there will be a different stack. Every thread has its own stack. Because you cannot interleave two threads execution stack together.
So
right?
this is the stack frame of the program. It may have different threads. Yeah.
No. This has
No. Okay. But they have different stack frame
yes
of different programs.
for different functions, not program.
Functions. Yeah.
Yes.
Different functions.
That function may be called by another thread. That function on another thread also has a stack frame. Yeah.
Right. What will be there in this libc libraries?
No, this is not code. This is stack. Library is code. This is runtime. This is a stack. This is some runtime data. This is code. The code doesn't change. Those are code are instructions. They don't change.
Yeah. They
Yeah, they don't change.
in the runtime.
Yeah, those are just for the local variables. Right? This function also may have its own local variables.
I understood that when I'm writing a code, that's a text.
Yes.
That is not changeable because that is a text. But when I'm making it a
It's
program,
not so. Well, for you to understand, you can say it's not.
it's a program.
Yes,
When I
it's a program.
execute it, it becomes a process, and
Yes.
process actually allocates a stack frame.
No, process has its own stack,
Stack,
or
yeah.
thread has its own stack. When we use the word stack frame, we usually talk about the function.
Function. Yeah.
Yes.
Sorry.
Yes.
So in a single stack, there could be several stack frames.
Many. Yeah.
Many. Yeah. So in that single stack, there will be only one library, right?
No, not necessarily. The matter of the library thing. Well, for example, the printf there could be, for example, this one can call printf, we can call string copy. Those are all library functions. Right? They're all library functions, but they're just functions.
So when we'll be doing the libc attack, so we'll be always
The thing is, when did you do that to export?
That export, I just did.
Just did it? The problem is this part, we don't have that environment variable. That's why I did it first. Yes. Yes.
I forgot about it.
Yes.
I'm gonna do it again.
Yes. That's why I checked if they're in both windows, both terminals.